digital twinning. Recent highlights include talks on digital twins for energy systems and digital twins for asset management at the 5th International Conference on Maintenance and Intelligent Asset Management, and that was in December 24. And also, he has the presentation titled A Case Study on the Use of Digital Twins for System Diagnostics in May 25. He was invited to present this also. Please join me in giving a very warm welcome to Professor Mishra, and we look forward to gaining valuable insights from one of today's foremost expert in digital twinning and its transformative impact on engineering systems. Professor Mishra.
Thank you. Thank you, Colonel Yadav, for introducing me, and thanks for such warm and kind words. My topic today, as you all know, is asset management through digital twinning. This is broadly in line with the main initiatives that Asset Management Society has been leading in this area. So many thanks to Professor Pai and Professor Gopi for encouraging me to give this lecture for this particular session. Although I'm on leave, I thought it was the best time because when we are working, sometimes it becomes difficult to get time to do these types of activities. So thank you very much. Again, I think although I have been introduced, I'll just reiterate that I'm within Department of Engineering, School of Computing and Engineering, and I lead Center for Thermofluids Energy System and High Performance Computing Research Center, and within that, Energy Emissions and the Environment Research Group that I'm currently leading. Now, my email and my phone numbers are there if any of you wish to get involved in the digital twinning activity further. You're more than welcome to contact me through my email or through just through the phone number. What I'll do is, if okay with all, I'll share my screen, and then we can start with the formal part of presentation. I'll try to finish in about 35 minutes, and then I'll leave last 10 minutes for any questions and answers. So that I think that will be the best approach. So let me share the presentation. Could you please confirm you can see that?
Yes, we can. Thank you.
Oh, thank you very much. Right. So the title of the presentation is Asset Management through Digital Twinning. Now, digital twinning has become a buzzword, although in the asset management area, there are people who have been working in this area for the last 20 years. At least I have been hearing the word digital twinning for the last 20 years. It's in the last 5 to 10 years, it has become a buzzword, and it is being used loosely in all sorts of contexts. So my attempt here would be to go through what digital twinning actually means and how it can be used for asset management. That is the core area of group activity for Asset Management Society of India. So just to give an overview, I'll give an overview of the digital twin and how we are implementing digital twin within the Huddersfield Smart House Research Facility, and then how this overall system works. And there are different components of digital twinning system. So I'll go through physical and computational system. I'll demonstrate flowchart of digital twin, and obviously any further work that we are doing, I'll give a glimpse of that, and then we can have a discussion at the end about different aspects of digital twinning. But I must mention that digital twinning as a word and how do we implement digital twin into the physical systems there is a big gap between the two. So in most of the literature that you see, there are lots of things about how digital twin can be developed and how it can be used, but you don't see many real life examples of digital twin. That is still quite hidden, or it has not become a common knowledge. And sometimes it is presented in a way that becomes very, very difficult for people to implement that digital twin system in their assets. So here I'll demonstrate that it is not at all difficult. It is very, very easy to create digital twins. Obviously, that depends on the level of sophistication that we wish to have, but it is not very difficult to create a digital twin of a system, at least at a reasonable level. And then we can always bring further sophistication with machine learning or artificial intelligence as we go forward. Now, it's a oft repeated topic what digital twin is, and it's very vague. You will find lots and lots of different definitions for digital twin. But at the core of digital twin definition is that we have a physical system whose digital twin we want to make, and then we have a virtual system that is representing the physical system. Now, when we say virtual system or computer system, what we mean is that this is the system that is representing the physical system, but at all these scales, and all the processes taking place within the physical system must be happening in the computer system in real time, almost at a same time. If not, then at least with some time lag, but this must be happening. So for example, if we take human body, now there are millions of processes taking place in a human body at a given time. Can we mimic that in real time on computer? All the processes from cell level to the um, um, macro behavior. It's very, very difficult. We need huge amount of scientific information, huge amount of computing knowledge to be able to do that in real time, even for a human body. So this is the best example of how complicated digital twin can be. But depending upon the application, suppose we just want to track motion of a car in real time on the computer, then it becomes easy. So depending upon the mechanics or the scientific information we want to represent in the computer system, this can be an easy job, or it can be very, very difficult task because the full scientific and physical information may not be available. But one thing is there, the third aspect of that is apart from physical system and the computer system, there must be interaction between the two. So if any change is happening in the physical system, that must be changing in real time in the computer system. And if we do change something in the computer system, that must modify the physical system. So then actual control must be happening between the physical system and the computer system in real time. That makes the digital twinning most complicated. And that is where many people take the shortcut of showing a simulation as a digital twin. So simulation is not a digital twin. Digital twin is where physical system and cyber system are connected with each other in real time. All the processes are mimicked, or reasonable amount of processes are mimicked, and both have capability of influencing each other's behavior. And the two connecting these two is cyber physical system, which is soul of the digital twinning. So cyber physical system connects cyber system with the physical system, and this has where lots of software, artificial intelligence, machine learning, everything, and you can embed in the cyber physical system. And more sophisticated your cyber physical system is, more effective your digital twin would be, more comprehensive your digital twin would be. So I think I have given a basic information about what a digital twin in general means and how we can define it. Obviously, depending upon the level of sophistication needed in digital twin, the task becomes very, very complex in terms of developing a cyber physical system or developing a cyber system. And even in physical system, developing proper instrumentation system for physical system. Okay, so I was mentioning about digital twin and common misconceptions that we have. So here with these three figures, I'm trying to explain what a really advanced digital twin means. So the first figure on the left, what we have is we have a physical system and then we have a digital system. So what happens normally is we have a number of physical systems. We have a wind turbine. We know how a wind turbine operates. And suppose we want to find out how the what are the stresses in the blades. And so we take the conditions of operation, we carry out FEA analysis in the lab, we try to find out how the blades are behaving. So in this manner, what we do is we do simulation in the lab of a particular physical component based on the boundary conditions provided by the operation in the physical condition. And this is what is typical simulation is. And we have been doing this for the last 50, 60 years in the domain of finite element analysis or computational fluid dynamics or dynamic analysis. We have been doing it all along over the last 50, 60 years. But that is not digital twin. That is simply numerical simulation of a physical system based on the likely operating conditions of that physical system. Now, the next advancement is where we have a physical system. So, for example, if we may have a wind turbine may have a sensor, the physical system may have a sensor. We take that sensor data in real time, create a numerical model, and use that sensor data as the boundary condition. So in real time, we can see in our computer system what type of stresses are being generated in a wind turbine blade or in a wind turbine system or a gearbox of wind turbine system. So that is real time simulation, but still that is not digital twin. So we are taking data in real time, we are implementing it, we are seeing in real time what is happening, but that is not digital twin still. So for digital twin, what happens is we must have the real time data from sensors coming into the physical system, sorry, coming from physical system to digital system, but then digital system is connected to the physical system. So based on the data that we are getting, if we need to modify the behavior of the physical system through digital system on our screen, we should be able to do that. And if any change is taking place in physical system, that should be reflected in our digital system in real time or almost real time, depending upon the sort of software and how quick respond our control systems are. So these are the major differences, or I would say, I will not say difference, but evolution, how things have taken on from normal simulation to real-time simulation to digital twinning, where it's not only real-time simulation, but also real-time control of the physical system and the ability of digital system and physical system to influence each other. So this is after this basic information, what I'll do is the smart house has been a cornerstone of our research activities in this particular domain. So I have taken a liberty of putting my digital twin, like not in actual digital twin, but some information on the about the smart house. So please listen to it. I hope you can hear it.
We're not able to hear, I suppose.
Are you not?
No, we are able to hear you, but not the video, audio in the video.
I think, yeah, if you go up to audio settings, I think you can say share my video sound, I think.
Okay, like if I'm not sure what I can do about this, but anyway, I think don't worry, I'll explain it verbally then. Is that okay?
Yeah, that's okay.
Okay. So yeah.
All right, go ahead.
Okay, no, I'm not sure how else I can share the sound. This is showing here though, but so not sure. Is there any other way I can do it? Okay, so what we have is we have a smart house here, which is a two-bedroom facility, which has been instrumented throughout. So in real time, we can monitor the data for the temperature, humidity, particulate matters. And in real time, we can take this data into a central hub through which we can upload it to the cloud. And then we can use that data as real-time boundary conditions for our advanced simulation. So basically, we convert about 10, 20 data to 10 million, 20 million sensors inside the smart house. So within the smart house, we know in real time at every corner how the indoor air quality is and how different parameters are changing in real time. And because we have a reasonable level of specialization in the computer simulations, then along with machine learning, we can develop data analytics to be able to control the systems within the smart house. The one of the main work that we are doing in this area is the combining physical sciences with the social sciences. So how the indoor air environment affects the behavior of the occupants. So that is the current area of work that we are doing. Also, we are combining it with the biological sciences that fine, this is the indoor air quality, how it may be affecting the health of occupants. So especially in the lungs area, suppose if we have particulate matter, how the particulate matters are moving and depositing in the lungs, and what type of effect they may be having on the cells of the lung. So all these things are the current area of work that we're doing. I'm sorry you can't hear this presentation, but I think I've given a reasonable amount of information about it. So just to begin this about the smart home technology, the theoretically smart home technology is defined as a home where we have automation to provide homeowners with security, comfort, convenience, and energy efficiency. So and an ability to control the devices that are within. So basically, a smart home is a home with sensors with which are connected through IoT and which can be remotely controlled through a smartphone or computer. That we can do now in our smart house. So we wanted to create a digital twin of a smart house, keeping in view that, okay, fine, this is a smart house. If we can create digital twin, our future aim is to create a digital map of the occupant and human behavior. So suppose if I'm occupying a smart house, what type of changes I may be experiencing, how my behavior may be affected. So that is the future area of work that we are carrying out, that we're planning to carry out going forward. But also, how do we support the aging population? Because the complex needs that aging population has, how the smart house can help us meeting those requirements without putting too much strain on our medical or health systems. So just demonstration of the physical system here, because now we are going into the digital twinning aspect. So just a demonstration of physical system. So one on the bottom, my right, this is the smart house within our lab space. Some of you may have seen it. And no, I don't think any one of you, but probably Jyotiji has seen it when he visited Huddersfield University. So this is the smart house, two-bedroom house, living kitchen area, 2 bathrooms here. And these are my team members who have agreed to act as a model here. So on a loose note. So and this demonstrates the sensors that we have put in all the areas of the smart house. Again, a different picture. So it is more interior. So this is the living area. This is the kitchen area. You can see we have a kitchen hood here. And this is designed to put different types of kitchen hood system and quantify the effect different types of kitchen hood designs may have on the extraction capability and the dispersion of particulates. So we are working with different kitchen companies, kitchen extraction companies on this area. Again, the toilet and bath for different, like for example, if for people with disability, how this can be modified so that it can be effectively used. Living area is normal living area, and then this is again the entrance of the smart house. Entrance is fairly important because what we have is here outside also we have lots of sensors. So not only we are mimicking what is happening inside, we're also measuring the air quality outside so that we can link the outside air quality with the inside air quality. Not only that, outside this building there is a road and there is an intersection, a roundabout. We are also planning to put some sensors there so that we can see, we can link vehicular motion with the air quality outside, and then what impact it may have on the air quality inside. We have a normal electric boiler there, but we are creating a capability of putting a heat pump on the parallel system so that we can provide a service to OEMs on heat pump. One more thing I must mention, that we can control the temperature of this smart house, inner temperature of the smart house, from about 2 to 3 degrees to about 25 to 26 degrees. So we can carry out tests on a range of products within this temperature range. And we can see the effectiveness of that smart house. So it has been in operation for 2-3 years, and I have been very happy to say that we have been able to get more than £1 million in funding. So lots of work has gone on in terms of industrial funding. Lots of papers have come out. Lots of students are completing PhD. So it is providing us a strong support in developing funding bids. So we have applied for an IHR PSRC funding bids in this particular area also. Currently the work going on. So you can see this one on the left here. There's bed here. So you can see some hanging wires here. These are thermocouples, and this work is done with a local radiator company. They make electric radiators. On the effectiveness of their radiators in warming the room, but what is the energy consumption that that radiator is having. So we can suggest them how many radiators to put, what will be the shape and size, and other details. We are also working with a mattress company on developing mattresses that are not only providing comfort while sleeping, but they also work as a diagnostic tool for the patient's health. So that work is also currently ongoing. Apart from that, we are working with a water monitoring system, a system that sort of predicts or informs in real time if there's a small leak taking place. And we are also working with currently some health monitoring companies where we are trying to finalize the arrangements with a health monitoring system. So we have lots of activities in the area of digital twinning, computational fluid dynamics, sound and acoustic engineering, and social sciences. So it's quite a successful adventure that we had, and I think it's going from strength to strength as we move forward. So now coming to the cyber physical system. So that is the physical system we had, the smart house with sensors. But then what are we doing with those sensors? So as you can see here, all these sensors, that about 80 plus sensors we have put, as you can see here. And all these sensors, right from motion sensor to temperature, humidity, CO2, 2.5, PM 2.5, VOC, and all these sensors are giving data to a wireless gateway, and from wireless gateway we take this data to cloud-based server, and from this cloud-based server we can take the data to our systems for further analysis. Now what you're seeing here is on the top left is another system that tells us about the thermal comfort, and it uses two parameters, what is predictive mean boat and PPD. I'm missing the name of the PPD, full something percent. And then we have the motion sensor, and not only that, we have instrumented the central heating system, so we can real time we can mimic or we can predict what is happening in the central heating system at which particular point. Just an example of how it is working. So as you can see, the top one is the temperature line, the middle one is the humidity line, and the last one is the motion sensor. So we have put motion sensors near the door. So someone entering the smart house will leave the digital imprint on through the motion sensor, and we can see how many people have entered when and all that. And then at the real time, we can also see nearby how the temperature and humidity are is changing. So what I'm simply suggesting here is that we can see how the human behavior or human motion or human presence affects the temperature and humidity. And this work we want to extend further and further to quantify. We also can see the motion in the kitchen area, and then we can see increase in the CO2 area. So human activity is increasing the carbon dioxide. And we all know that if carbon dioxide concentration goes more than 800 ppm, it may start to affect uh, the the experiences or the feel that we have. So just an indication of testing the sensor system and how the sensor system is behaving. Is it accurate, and can it be relied on for further analysis? Again, then particulate matters 2.5. Actually, the particulate matters are one of the most important um, variables that need to be monitored, because what happens is as the particle size becomes smaller and smaller, especially in this area, 2.5 micron or something, once they go to the lungs, it becomes very difficult to sneeze them out. So if there are bigger size particles, you can sneeze them out, but if there are smaller size particles, they do affect the lung capacity, because once they are gone there, they don't come out there. So it is very, very important to monitor the particulate concentration. And again, how the human behavior, human action around it is affecting, we can correlate the two. Okay, so that is the physical system that we had and the cyber physical system. And we wanted to include the more software power to it. So what we did was we included the simulation capability alongside our cyber physical system. So in our cyber system, we had this simulation capability, and then we also included controls like in terms of lighting, ventilation, and access capabilities inside. So that is a framework of our digital twin, a general framework of digital twin. So we had a couple of computing facilities like CFT and LBM, and then we had multiple controls that we included in the digital twin. So I mentioned about the three most important sensors. So temperature, humidity, and velocity sensors we included there in the cyber physical system. And then we also used MATLAB as the software control system. So MATLAB was used to integrate the cyber physical system with the computer system. So all the controls of the computer system, all the controls in the controller were operated through MATLAB in this particular work. My what I'm planning to, like in this discussion, what I'm planning is that you can see that how easy it is to create a small scale digital tuning system. Obviously, we can make it more complex as we go on, but if you are making a start, you can create a very small digital twin system with not that much of difficulty. It is not as difficult as sometimes people make it to be. Okay, so here what I'm showing is the computer model of the physical system. So you can see that we have taken almost full details of the physical system into our computer model. Obviously, there are some simplifications because the actual physical house may have lots and lots of geometric variations, and some of those variations may not be needed at that level just to help with our computer simulation. So in the left bottom is the digital twin model, which is fair, I would say. It's about 95 to 99% similar to the physical model, with all the even internal details. As you can see, we have even modeled the furniture, the staircases, and all the other details. We have modeled it. On the right side, I'm showing that this type of things are happening already in case of the aeroplanes, the jet engines. As you can see, most of the jet engines used have the digital system, not to that much detail, but reasonable amount of detail. And the these air companies can in real time monitor the performance of their jet engines. So they have the operational history of all the engines. They have maintenance history, real time operational data, the FMEA, CAD model, and FE models. They are all combined, so they already have this. Now we're trying to do similar things with the smart house. Okay, so how did we plan this digital twin for a smart house? So basically, we had a physical system, and then we integrated this physical system with the lots of sensors, and then we put controllers. So we use wireless ESP32 controller to link the physical system with the computer system. And this controller was controlled by MATLAB code, as I mentioned. So we use MATLAB as the base code for linking cyber physical system with the computer system. And we used ANSYS Fluent as the computer system, which could in real time, almost real time, predict what was happening inside the smart house. And then we calculated the thermal comfort. And based on that, we used a controller that controlled the opening of a window to maintain a particular condition inside the smart house. If that condition is not met, it will keep on changing the window opening condition till that condition has been met. So this is a general framework of the digital twin that we have created. It was very, very important for me to have the computer system working, because if our control system is going to work on the data analytics from the computer system need to be perfected. So this just shows the ground floor and the first floor plan of our smart house, and then how we operationally use this information to define the boundary conditions for our simulation model. So we used like, where is the airflow is coming from? Is there a radiator? How is its temperature changing? What is the behavior of the walls? What is the U value? And how the air is going out? So we defined inlet and outlet. We defined any sources, and we also defined the conditions at the wall before we went in the analysis domain. And then we checked it. Are we getting the real data? The data that sounds reasonable? And we could check that, okay, fine, the air distribution, the temperature distribution seems like what has been observed by others. So this increased our confidence in the simulation methods that we had. So this is simply on the flow from inlet, a constant flow. Now, but then again, we simulated the opening and closing of the doors, and based on the motion sensor data, and tried to see that whether we can simulate any dynamic situation, for example, person going in or coming out. Once we have done that, then that was the normal flow model. We didn't include temperature effects, but then we also wanted to check the temperature effects. So there's a radiator here, which is, as you can see on the left, there is the temperature of the radiator is changing with electric supply, and we wanted to see its effect in real time on the smart house. So again, we worked on the effect of heating on the temperature distribution, but also on the velocity distribution in terms of the buoyancy effects. So once we have perfected this, then we put variable conditions on the radiator and try to map the temperature distribution on the radiator. So this is the complete flow chart of the digital twin. The bottom left is the physical system. So we had sensors for distance, temperature, and humidity. And we had a controller that could open or close the window system. We had the MATLAB environment that took the data from, that controlled the controller, but took the data from the physical system. And this data was in real time conveyed to the computer system. The computer system created the simulated the conditions inside, and based on this condition, we predicted the PMV value, that is mean mode for thermal comfort. Based on this condition, then it went into MATLAB environment, and in the MATLAB environment, then which we could open or close the window, and then that information was fed back again to the controller through to the MATLAB, and then again simulation was repeated. This process was repeated till the required conditions met in the smart house. So this is the physical system, this is the cyber physical system, and this is our computer system, three distinct zones, and just we managed all this through MATLAB environment. Now I'll demonstrate the operation of digital twin. Some of you may be seeing it for the first time. So let's, it doesn't have sound, although I think one of my PhD students put some music behind it. So you may not be able to hear the music, but you will be able to see how a smart house operated, a digital twin, a smart house with digital twin operated to achieve a PMV value. So there is an initial window opening, we calculate PMV, we see whether PMV is at a particular value or not. If not, then it will change the opening of the window. It will keep on doing continuously till we meet the requirement. There are subtitles in there, so you can read that. I don't think it requires any direct intervention from me, but at the end, if it's needed, I can always explain that. So it's a quick demonstration to you for how digital twin worked in that case. And finally, at 0 centimeter, we found that PMV is adequate, and there is no more intervention needed. So this is just a simple demonstration of how digital twin can be used, can be made. And we have done similar work in other physical assets, for example. So we have also created a digital twin of a control valve, in which we have a valve provided by a local company, and we put sensors around it, And in real time, we can see performance of the valve, and we can embed data analytics inside to see whether valve is performing correctly or not, or if it is not performing correctly, what may be the problems. So we have used exactly same principle. So this technology can be used in almost all spheres of process industries. People are using it for infrastructure industry also, in terms of lots of work is going on in the roads, buildings, critical infrastructure, to see in real time how things are happening. But in terms of mechanical industries or chemical industries, we can work with valves, pumps, pipes, turbines. We can create digital twinning of all such systems. And lots of activities is currently ongoing. We are doing our bit in terms of some of the areas where we are working. So so from a smart house to control valve to wind turbines, we have been fairly active in this particular area. And like it's very sort of good that now we have demonstrators for a smart house and the valve in our lab. So more than welcome to come and visit us, see how these systems work. But if there are opportunities for collaborating with industries and academic institutions, I'll be very happy to collaborate in these areas and support further development. So thank you. Thank you very much for listening to me patiently. I'm very happy to answer any questions that you may have. Thank you.
Thank you, Professor Rakesh.
Thank you.
It's a wonderful presentations as always. So I'm very happy that some of my students are very much interested to know about it, and some of them have joined also. So I'd be looking forward to getting your involvement with some of our students' activities. We may be coming to it later on. Thank you very much for this lecture.
Thank you. No problem. Thank you.
I'd just like to say thank you very much for that, Professor Mishra. I think what was refreshing for me, in Australia at least, we spent a lot of time in digital engineering and BIM, and unfortunately it only gets value during design and construct, and then all of a sudden you're left with a model that isn't really usable. But I really appreciated what you showed today, how you can bring it together in a living, breathing system. So a lot of the principles of what you shared today, I'll take that back to some of my colleagues as well, to look beyond just the BIM and to look at a system point of view. So thank you very much.
Thank you very much. And in fact, currently we are working with a combination of BIM plus, because in BIM you have energy modeling. So in my team we have a researcher. She has an architectural background actually. So she's quite an expert in BIM. So we're combining BIM with the CFT and energy modeling. But what we are trying to also to do is in real time to predict the operational efficiency of the buildings and life cycle analysis of the buildings in real time through this. So
Right.
yeah, so I think BIM can very effectively be used with this for variety of purposes, because as you rightly said, we build the building, that's fine, but we don't focus that much on the operational aspects of the building through the digital tools that are available. So in fact, we are currently working, we have initiated discussions with one of the partner universities on digital twinning of high-rise buildings.
Okay.
So that in real time we can not only positively influence the operational effectiveness of the buildings, but also minimize energy consumption, improve indoor air quality, and all that. So we are currently developing a tool for that particular purpose.
No, thank you.
Thank you.
Thank you.
Yeah, thank you, Professor Mishra, for the excellent presentation and how asset management can be done using digital twins. One question that comes to my mind is what about the security issues, especially when you're talking about a house where people live or a multi-story building, and you are integrating it with sensors and then making it open to the digital world, because as most of us belong to a generation where we are very comfortable with the physical systems. For example, if I want to go to a bank, I'm still comfortable presenting a check rather than doing my transactions using. Of course, it's quite easy and there are a lot of benefits, but the kind of things that are happening with the digital banking, a lot of people are losing money. So, what kind of security protocols or is it required, or how are you going around doing the security issues concerned?
No, it's a very important question, Professor Pai, and I would not like my house to be remotely handled by someone else, obviously. So digital security, cyber security is very, very important. And because in digital twinning, the cyber system is a very, very crucial aspect. We are working with other teams within the university, but that is not part of my domain, my expertise. But we are working with other teams on how do we use the industry standard security methods within the digital twinning. Now, my initial first work was to get a digital twin and get it to work. So now we have achieved that, and now we are working with other teams on how to make it more secure. But moreover, how do we create more use cases? Like having a digital twin is fine, but if it's not giving any return on investment to an industry person, there is no use for it. So we're trying to develop use cases where it can be useful. Some of the uses are quite obvious, but in normal, can it be used for futuristic design? Can it be used for modifying the design? And so all such cases are being worked on, but we're working with the cyber also aspects also. Not my team, but I think a parallel team within the university.
Thank you. Professor Mishra, you wanted to ask a question.
Yeah, how are you, Professor Rakesh? After a long
Thank
time,
you.
we have been meeting though
Yeah.
virtually. It's always
Yeah.
wonderful listening to you and your uh, research, what you call contemporary and even very, very interesting research that you're making. But
Thank you.
I always ask a very simple question when we talk about digital twin or even cyber physical systems, like Professor Pai was mentioning. I will add to that one is about your privacy when we talk about social systems. So social systems, cyber physical systems, digital twin, these are very intriguing parts of our social life so that it has to be embedded in a seamlessly if it is possible. That's one part. Second part is that, what could be the total cost of ownership of this transformation? And can we actually come up with a business model where startups can come in and it can actually be internalized by the industry or even youngsters to see that there is a business model behind it. That's the other two things I would like to flag.
Yes, thank you very much, Professor Mishra. It is always wonderful seeing you and meeting you again. So it's a pleasure. Regarding the privacy aspect, you're very, very right, because I think the initial use case that we thought was to support people with dementia,
Yeah.
or where like where these types of interventions may be needed, but then privacy becomes an issue. So how do we effectively implement digital twin keeping privacy in mind is a different subject area altogether. So we have been doing some work in that area also. For example, there is no video recording, there is no video inputs, things like that. It's only the sensors which give information about what is happening, but not in a very intrusive manner. So that is an area of work that we are carrying out, and that must be taken into consideration because of the privacy issue. Regarding the business model, you are very, very right. I think that this is right now lots of work is scientifically going on in creating business, in creating the digital twins, but the business people have not worked closely with in the scientific area to create use cases, and that is exactly what we are doing. So, for example, in the area of valves, we have worked with a local company, and we have demonstrated that how much um, money will they save. In fact, we have been able to develop a tool for real-time diagnostics using digital twin. So they can get information in the real time, but how to quantify that information in terms of return on investment, these types of work, I think probably we need to collaborate more with the people with the business, and we need to create that.
Are you planning for any incubation or are you having an incubation center there?
Yeah, I think if I was 20 years younger, I would have opened a startup. Or maybe we can take inspiration from Professor Pai, who's a successful entrepreneur. But there was a thought of doing this, but I think one of my collaborators, a student who is working now in another university, he has thought process of developing a company around digital twin tools. So he has requested me to become partner. So this is what we are exploring. So there is a chance that we have got some business from a high-rise building company's owner, and they want it to be implemented. So we're working on it. There is a possibility that we will enter into that.
Yeah, Shubham Sarkar, you put up your hand.
Yes, sir.
Can
I
you put
wanted
your
to
video
ask,
on?
sir, right now means I'm not in means perfect place
Okay.
to show.
All right. Okay. Go
So
ahead.
my question to Rakesh Mishra sir is means I have worked recently on some basic VR simulation. So I'm really curious about the intersection of digital twins with immersive technologies like VR, AR. To enrich the visitors experience and all that. So means I am not that knowledgeable, but I'm very means interested in knowing that. So can you means tell me a little bit?
Yeah. So like if you have the physical system, which is properly censored up, so and you're getting data in real time, and if you have a computer model of the physical system, it may be through virtual reality also. And if you can overlay your virtual reality model with the sensor data to demonstrate what is happening in the real time, then that is of some use, because then you can in real time in the mixed mode show the details of things or phenomena happening in the physical system. Now, what you do afterwards is a bit difficult, but at least at this stage, you can use virtual reality to showcase the phenomena happening in the physical space in a more detailed level. We have done some work with virtual reality. So that is useful to display what is happening inside. But control aspects you have to work on.
Okay,
Yeah.
sir. Understood.
Professor Pathak.
This is exactly one thing, Professor Kumar, that as Shubham was telling, he is my student only. Now he started working in that line. Now, what you may be knowing in sometime in our asset management society, we were talking about our this campus assets. So this digital twin of our water treatment plant and sewage treatment plant. Exactly one of the major cost center of the institutions where this maintenance is always gives a other type of problem. So I was trying to get my students involved in the understanding the machinery of this water treatment plant in the, like in Kharagpur type of campus, where we bring water from 20 kilometer away with a number of pumps on the road, then pipeline, and then we have got a total water treatment plant. Now, if we want to develop a digital twin system for the that our predictive and prognostic maintenance of this system, I would like to see that if there could be a collaboration in developing and incubating a company, that which we were telling sometime, with our enthusiasts, that is entrepreneurship oriented students who are working in this. So in that, your Hudson University and IIT Kharagpur together in our research park, how can we go ahead with it? That was what exactly. And then today, I think a couple of my students from mining machinery and all are there. They are listening to you. And that Shubham, he is there. He's already taking as a intern. He's working with our ex-layer at our research park also. with say some new startup company. So I identified this area for our campus asset management, how digital twin can be put into prognostic maintenance of our water treatment plant and the sewage management system. On that, we need your suggestions, undertaking, and how you can get involved into this whole problem.
Yeah, thank you, Professor Pathak. It is always a pleasure to discuss with you various technical aspects, and I think we have been speaking about various aspects of digital twin for a long time, and it would be a pleasure to get involved actually. So, like I think you have really identified a very good problem. Thinking about it, if we can develop a tool for prognostics management, or sorry, prediction of the condition of the water treatment plant, and if this startup company can develop a tool for that, it can be very easily scaled up across a range of councils, range of institutions. And the main thing here is that exactly identifying that we want to create a digital twin for which purposes. So, if, like for example, are we going to monitor the water treatment process, or we are going to monitor the instruments that are used in the water treatment process? And then we can define sensors, where to operate the sensors, how to create digital model, and then how do we get the information, and then how do we use that information? So all these things can be carried out. Possibly, we need to have a chat about, do we need an MOU between IIT Kharagpur and Huddersfield University, my team here? Once we have established an MOU or something like that, then we can develop the detailed plan of how we work together in that. So I think possibly we will need a bit more detailed discussion beyond this, Professor Pathak. Is that okay?
Okay, thank you. Because already our one startup company has formed on that line. So only thing is that digital twin part, how to get it incorporated with your expertise. So
Yeah.
we'll carry forward to this one.
Yeah.
Yeah,
So
one last question from Colonel Sunil Yadav, and rest of the questions can be directed to Professor Mishra directly. Oh, there's one more from Professor Jyoti Sinha. I think Colonel Yadav
Yes, sir.
can go first. Yeah.
So my question is regarding it's coming from the defense systems. Can we have a digital twin for a missile system, and how it can help in testing of a missile when it is being fired? That is one question. And how it can help in making a simulator for training for a system like a defense system like tanks or anything like that.
Yeah, so the first question, I'm pretty sure that with all these missile interceptors and all that, you already have most of the defense systems would have a simulator to see the trajectory of the missile, the reach and length, and all that things may already be there. Yeah, like if you want to add much more detail at this, I think at the operational level, only few data points, that is trajectory and the location and how it is going is there, but I'm pretty sure that in the defense circle this will be quite advanced already. But we can at the theoretical level, the creation of a digital twin, at least at a reasonable level, should not be that difficult. That, like, I don't have much information about how it is used in defense system at the moment, but I'm pretty sure they would have a reasonable digital twin of missile systems already. I feel so.
Okay, so I'm not aware. I thought maybe they have simulators. I know about the simulators, but not a twin per se, as you have explained right now. No, so you are measuring the trajectory, how it is the thrust of the missile, direction it is taking, the continuous feedback which is coming, how it can be further change and autonomous decisions if something has to be taken in between, like you want to. These systems could be there, but not to the extent which you had explained in your smart home system. From that perspective, I thought maybe it can be further improved.
Yeah, it can definitely be
anything
improved. Yeah, just to like going from 90% effectiveness to 100% effectiveness of a missile shield system, for example, that will require digital twinning of the entire sphere of operation. So I think that is. What was your second question, Karnal Yadav?
Second was that with this digital twinning, can we improve our simulators now?
Yeah, I think
Simulation
that
of
that we can definitely do. We can put more and more details into the simulation, so that we can increase the spatial and temporal accuracy of the system. So that we can definitely do by putting more sensors and using more complicated or more complex, not complex, but more effective simulation models. So we can definitely do that, I think. So
thank you, sir.
I'll be very happy to support any initiative in these areas with the team.
Thank you, sir. Thank you. Get back to you.
Yeah, Professor Sinha.
Right. So thank you very much, Professor Mishra, for your excellent talk. And I have seen the facility, so I can able to relate to what you're speaking about. I'm not asking the question. I have just my own experience. I just want to add the comment. Digital twin is really look like very nice word, and people like to, and industry may be very much excited because industry always want to use black box to do all their work. But the problem with the digital twin, what I see is a simulation. You can get the physical model very quickly, but simulation is going to be very difficult part. If the system is deterministic, simulation is going to work. If system is uncertain, it's difficult. I'm coming from a maintenance background and industry person. Simulation, if you want to do some maintenance, when we need to do this maintenance, when we intervene something to stop, that kind of simulation in the industry is going to be difficult. Another thing what I see is like if I'm talking about diagnosis of the machine, in a industry, identical machine, exactly identical machine, maybe 10 number, 20 number within an industry. If we use simulation for one machine, it may not work for another machine because of different conditions, a different boundary, different installation, maybe all put in the series or maybe all parallel connections, but because of different things. So this is just my comment. So I don't know whether this kind of digital twin is going to be useful for all kind of system, because I can see the industry people are very excited to know that they think that they can do everything as a black box. But this is somehow my limitation. I can see even my PhD students and everybody is working, they are struggling. So this is just a comment.
Now,
No,
just to add to that, coming from again a background of tribology, maintenance, friction wear, when you talk of mechanical systems, friction is always going to be there, and friction behaves differently at a macro level and a micro level. Sometimes it's opposite. And studying friction, people have spent lifetimes. So just as Professor Sinha just mentioned that conditions, that's the reason, why machines, the same machine made, in the same factory, maybe installed in different, they have got different lives. Even our own motor cars, you will see, of course, the usage also matters. They behave, ultimately, it is something that's happening between two surfaces that are moving past one another and a lubricant in between them. So yeah, modeling and simulation, as Professor Sinha said, yes, I think people are excited about that. But when it comes to mechanical systems, there could be quite a few challenges. Yeah, but that I think will take some time for us to come across and how to go about it. I'm not sure whether it'll be in 5 years, 10 years, or whether we'll be around to do that. Maybe the younger generation should be looking at some of these things. So that's just a few thoughts of mine. Yeah, I think
I completely
Professor
agree
Mishra,
with.
yeah.
Sorry, I completely agree with whatever Professor Sinha and whatever you said, Professor Pai. 100% I agree. there are ways and means of alleviating some of the problems and pains that happen because of the micro behavior. So like if you're creating a digital twin for a macro behavior or a micro behavior, at what level we want to do that, it all depends on that. So in a broad sense, there are digital twins already operational, like for example, jet engines and other things for macro behavior. But if you want to go for micro behavior, root cause analysis or initiation of a fault, these are the very complicated areas. And for that, you need to have simulation at that level. And many times the physics itself is not known, like you said about friction. So in those cases, I don't think it is of that much use. But now one thing has come recently is that machine learning and artificial intelligence. So what we are now doing is, in place of, because simulations take time, there is a time lag behind it. So now we are also implementing data driven methods, and like Processina, and you have worked on it for long time on predictions and maintenance and all that. Now data driven methods are being used. So we're trying to use data driven methods to speed up the process. But one thing must be there, that it is not the solution for everything. It can do some things reasonably okay, and then we can try to make it better so that we can make it make its use more effective for different applications. So
Exactly. So one of my students, they are not using simulation, they are using data-driven model to predict when maybe maintenance is required, what is the time duration required for those kind of predictions, but not by simulation based on the previous data from the industry.
yeah. So that is the best approach. So we have been doing certain things, like in where we have been able to get the physical knowledge developed to go towards the initiation of fault. So for example, if you know that in this domain there is some particular problem, so in place of overall simulation, just focus on certain aspects, and make your resources available for that particular aspect. So it is very difficult, like the limitations that we have in terms of the resources, computing resources, simulation resources, and all that. It will be very difficult to have entire system simulation in one go. But we can always use data-driven methods alongside some of the simulation methods to focus on to the areas where we need to focus on.
Yeah, one last question from Professor Chattopadhyay, and after that, any questions can be directed to Professor Mishra.
Thank you. I think it was excellent presentation, and I thoroughly enjoyed. Only one thing, what you mentioned, I think, in terms of the root cause and physics, and many times these are not known. And definitely when the knowledge is known, the mechanisms are there, then the preference is that how to improve that one, because always the confidence level will be less with the limited knowledge what is at this moment. How much effort and cost will be there to update those things once this, like, let's take into my area like a rolling contact fatigue, and in terms of your surface cracks and the subsurface cracks and how you look into those things, and then intervention actions, what Professor Sinha was talking about, those types of things. Many times it's not known yet. And then when it is known, will it be to start afresh from that, or you can also use what is developed and further enhance that one? So what is your gut feeling in that area? Thank you.
It's very good question, and I think it is very thought provoking also. So the main thing is, in my view, my personal view, I see it as a, like how the physical sciences have evolved from Newtonian mechanics to, we are now going towards quantum mechanics. So basically, we can develop a framework of microscopic behavior. So in terms of the macroscopic behavior, overall system behavior, we can easily model through digital twin. But more detailed physical sciences can be a subset of this macroscopic behavior, and we can embed knowledge as and when it becomes available and link it with the macroscopic behavior. So this way we can have a different layers of digital twin, and I can't say I have coined the word, but I have been using the word multi-layer digital twin, depending upon at which layer you want to work. So you can start with a very macroscopic digital twin, and then we can keep on adding different layers to it depending upon the information that becomes available in time. So then it can be slightly more future proof in that sense.
I think that's a good approach, and that is where you don't have to throw away everything, and you can build on that, and like some of the modules, and then layer by layer. So that makes sense. Thank you.
No worries. Thank you very much.
Professor Ganesh, can you please give the vote of thanks?
Yes, sir. Am I audible?
Yeah.
Yeah. Good afternoon, everyone. On the behalf of Asset Management Society India, it's my privilege to extend a heartfelt vote of thanks at the conclusion of today's enlightening webinar on asset management through digital twinning. First and foremost, I extend our deepest gratitude to Professor Rakesh Mishra for delivering such a insightful and thought-provoking talk. Your expertise, drawn from years of research and practical engagement, has given us a comprehensive understanding of how digital twinning can be transformed to the future of engineering asset management. I would also like to thank Professor Raghuveer Pai for a warm welcome and throughout this session asking good questions and monitor and controlling this session. And also I thank Dr. Colonel Sunil Yadav for the introduction of our distinguished speaker. Our sincere appreciation goes to all participants who joined us today. Your active engagement through your presence and question and answer session has made this session interactive and meaningful. A special thanks to the organizing team and the technical team AMSI India for smoothly organizing this session. Lastly, I thank the Asset Management Society India for continually fostering such a valuable platform for knowledge sharing and professional growth. With that, we conclude today's session. Thank you once again, and we look forward you in the future webinar. Thank you.
Thank you. Thank you all.
Thank you very
Thank
much.
you, Professor
Take care.
Mishra.
Thank you. Yeah, thanks. Bye. Bye.
Thank you. Bye.
Thank you, sir.